Hi, today we're going to be talking about the law of total probability, as well as Bayes' theorem and Waring's theorem. So the first one is the law of total probability. So we're going to let B1, B2, B3 going on be a collection of events that are pairwise disjoint and exhaustive. So pairwise disjoint means that none of the pairs overlap, so they have the intersection is 0, and exhaustive means that the union of all these events is equal to the whole sample size. These events span the whole sample size. So we have an event A, and we're going to say that the probability of A, is equal to the sum from n equals 1 to infinity of the probability of A intersection Bn. We can further say that the probability of A is equal to the sum of the probability of A given Bn times the probability of Bn. So this can be quite confusing to think about, so let's look at an example. So here, this whole block represents the sample space, and I've drawn all these different events, B1, B2, B3, all the way up to B7, and then I also have A in pink. So we're trying to work out the probability of A, which is here. So we're going to add up all the probabilities of A and Bn, so every time an A intersects a Bn. So let's first have a look where A, I'm going to do it in green, let's do it in highlighter. So let's first have a look. So I'm going to have a look where A intersects B1. So we can clearly see that A intersects B1 over there. And now we're going to have a look where A intersects B2, which is here. A intersects B3 here, A intersects B4 is here, and A intersects B5 is here. A intersects B6 doesn't intersect, and A intersects B7 is also doesn't intersect. So we can clearly see that by adding up all these different parts, by adding up this part, and then this part, and then that part, and that part, and that part, we get the full probability of A. Now let's look at an example. So let's say a bag contains 7 red balls and 5 blue balls. You draw 2 balls at random without replacement, one at a time. What is the probability that the second one is blue? So first let's let B1 be the probability that the first ball is blue, and B2 be when the second ball is blue. So we want to find B2, that's what the question's asking. It says the probability that the second one is blue, so we want to find B2. So we know that the probability of B2 given B1, so the probability of second ball being blue, given that the first one's blue, is 4 out of 11, because altogether there's 12 balls if you add 7 and 5, but now the first one was blue. So now there's only 4 blue balls left out of 11, so that's why it's 4 out of 11. So now we're going to look at B2 given B1 complement, so given that the first one was not blue. So if the first one was not blue, that means it was red, so that means we drew a red one on our first one, that means there's 6 red and there's still 5 blue. So that means there's 5 out of 11. So now we have these conditional probabilities. B1 and B1 complements are mutually exclusive and exhaustive, so they have no overlap and they cover the whole sample space. So now we're going to use the law of total probability. So I'm going to say the probability of B2 is going to be the probability of B2 given B1 times the probability of B1 plus the probability of B2 given B1 complement times B1 complement. I like to think of this almost as a bit of a weighted average. That helps me to remember this kind of formula. So we worked out earlier that this probability is 4 out of 11, and we worked out that this is 5 out of 11. The probability that the first ball is blue, you can just look at the question, there's 5 blue, 7 red, so it's going to be 5 out of 12, and the probability that the first one is not blue is 7 out of 12. When you multiply all of this, you get that answer. So that's quite a simple example using the law of total probability. Next, we're going to be looking at Bayes' theorem. So Bayes' theorem says let A and B be events with the probability of A times the probability of B being greater than 0. This basically just makes sure that the probability of A and probability of B are both not 0. Then we can say that the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. So this is just a formula. So now let's see an example where we can use it. So continuing from above, now we are given that the second ball is blue. What is the probability that the first is also blue? So now we want the probability that the first one's blue, B1, given B2. So we can say that the probability of B1 given B2, using Bayes' theorem, for the first one you swap them, so it's B2 given B1 times the probability of B1 over the probability of B2. So we know the probability of B2 given B1, we worked that out earlier, is 4 out of 11. Probability of B1 we saw earlier is 5 out of 12. And the probability of B2 is what we worked out in the previous example, was 55 over 132. So that's how we get that. And then overall we can see the probability of the first one being blue, given that the second one is blue, is 4 out of 11. Finally, we go on to Waring's theorem. So Waring's theorem says we have events A1 all the way up to AN, and we're looking for the union of these events. So we're looking for the union of A1, union A2, A3, A4, all the way up to AN. And Waring's theorem says that to find this union, we can use this special notation where we have Sn1 minus Sn2 plus Sn3, and it keeps alternating. So it'll be minus, plus, minus, plus. And this number at the bottom, 1, 2, keeps incrementing until it gets up to n. And the way we define Snk is the sum of all probabilities of intersections of k events. So this can be a little bit confusing to think about, so let's look at an example. So let's look at the intersection, the union of 3 events. We're going to look at the union of A1, A2, and A3. So using Waring's theorem, we can see that there's a total of n. So at the top we're going to have 3's, S31, S32, S33, and it goes all the way up to 3. So it goes S31 minus S32 plus S33. And now, S31 is where we all have one intersection. So it's just all going to be probability of A1, A2, and A3. So now S32 is where we have 2 intersections. And that's going to be probability of A1 and A2 plus A1 and A3 plus A2 and A3. And finally, S33 is just the intersection of all of them, A1 and A2 and A3. So that's a simple example of how you would apply Waring's theorem. Now let's have a look at a real life example. So consider 2 identical decks of n cards, each numbered 1 to n. Suppose the decks are randomly shuffled and placed next to each other. A match is said to have occurred if a particular card occupies the same position in the ordering of both decks. What is the probability of at least one match? So for example, let's say we shuffle the 2 decks and there's a king of hearts in position 13 of both decks. That would be a match. So we're looking for the probability of at least one match. So there can be 2 matches, there can be 3, but we're just looking for at least 1. So we're going to start by saying let AN be the event that a match occurs at the nth position. Okay? We want to calculate the probability of so AN is the event that a match occurs in the nth position, and we don't care where the match occurs, just that there is one match. So we want the probability that it occurs in the first position, or the second position, or the third position, all the way up until the nth position. So that's what this means. We're looking for a probability that occurs in any of the positions. So now we need to find the probability of AN. So we know when we arrange n cards, when we shuffle them, there's n factorial ways to arrange them. But now that we want a match, we have to fix one of the cards in this particular position. So by fixing this card, in our numerator we're going to have 1 fewer possibility because that one's fixed in place now. So we're going to have n minus 1 factorial over n factorial. Now we're going to look at 2 matches. So here we had 1 match, now we're going to look for 2 matches. So here we have 2 matches, AN and AM. So now we fix 2 cards, so now we're going to have n minus 2 factorial over n factorial, because now we keep 2 in place, now we only have n minus 2 factorial cards to shuffle around. So these are just the first 2, now we're going to do it in general. So for as many matches as we want, we're going to say the general formula is n minus k factorial over n factorial. So now we have a general formula, but now we still need to find our s's, our Sn1. So let's first have a look at Sn1. So Sn1 is going to be the sum of all your probability of AKs. So it's going to be n choose 1 times n minus 1 factorial over n factorial. And we know that n choose 1 is just n, so it's going to be n times n minus 1 over n factorial. We can split n factorial into n times n minus 1, so overall it gives us 1. So now we need to do it in general. So that was just for the first one, just an example. So in general, it's going to be n choose k times n minus k factorial over n. So we know if we expand the choose function, we can expand it to this, and then we can cancel these n's, and we can cancel these n minus k factorials, and we're just left with 1 over k factorial. So now this is the thing we're looking for altogether, that there's a match in any position. So we're going to use Waring's theorem. So it's going to be s1 to the power of n minus s2 to the power of n plus minus all the way up until sn to the n. Snn. So we know that Sn1 is going to be 1, and then Sn2 is going to be 1 over k factorial, so it's going to be 1 over 2 factorial, plus 1 over 3 factorial, minus 1 over 4 factorial, plus all the way up until 1 over n factorial. So that's the answer to this question. Check out the rest of my videos and enjoy the rest of your day.